Hello, my name is Silvio Dobrota, and I will be presenting to you my PhD project. We are always hearing from the media how the concentration of carbon dioxide in the atmosphere is increasing and contributes to the more severe weather events such as floods and prolonged bushfire seasons. Severe droughts often increase the severity of bushfires, which are considerable emitters of carbon dioxide. The Paris Accord is the most significant global commitment to lowering carbon dioxide emissions. Unfortunately, the targets that nations commit to are non-binding. Very few member nations have committed to ambitious targets. Carbon dioxide has been considered an ideal carbon-1 synthon feedstock in the synthesis of commodity chemical products. Carbon dioxide is non-toxic, cheap, renewable, and it offers a pathway to the sought-after circular carbon economy. The more obvious reason is that we have too much of it in the atmosphere. Some of the possible compounds that could be produced from the activation of carbon dioxide are acrylic acid and propiolic acid. In 2014, almost 6 megatons of acrylic acid was manufactured. It is used in the manufacturing of superabsorbent polymers, surface coatings, adhesives, and many others. Propiolic acid is used to make polymers, coumarins, antifungal agents, and others. There have been several studies into the reactivity of organometallic complexes towards carbon dioxide. Dr. Peter Jerd from the field group has worked extensively during his PhD on iron complexes. These types of reactions all follow a similar sequence of steps. First, you need a co-substrate, such as ethylene, to react and bond with the reactive precursor complex, in this case the cyclomethylated complex. This produces the ethylene complex. Carbon dioxide can form a carbon-carbon bond with the ligand, followed by cyclization, which leads to the formation of the saturated metallolactone iron complex. The next step is to cleave the cyclized ligand, which is usually done by deprotonating the beta carbon, leading to the formation of the acrylato hydride. The final step is to regenerate the catalyst by releasing the acrylic acid from the complex. Two possible methods were reported, but unfortunately none of them offer a catalytic cycle. When UV radiation is used in the presence of ethylene, although the catalyst gets regenerated, the formation of acrylic acid is not observed. The second method uses a strong base, such as sodium bis trimethylsilyl amide, to cleave the acrylate. This gives sodium acrylate product, but also degrades the organometallic complex. These sort of reactions have been explored for acetylene as well. This acetylene DP complex can be synthesized from the cyclomethylated complex to give this acetaldehyde complex, which can react with CO2 to give the unsaturated metallolactone complex. This ethylene complex was found to couple CO2 to ethylene and thus catalyze the formation of potassium acrylate. Step A is the CO2 coupling and cyclization. Step B represents the cleaving of the metallolactone and the formation of the acrylato hydride complex. The final step C involves the deprotonation with potassium ethoxide, which regenerates the catalyst and releases potassium acrylate. I will briefly outline some of the aims of my project. I will work on the synthesis of novel organometallic complexes which have the potential to catalyze the conversion of carbon dioxide to commodity chemicals, focusing on iron and ruthenium complexes first. Where necessary, I will look into ways of improving the purity of the product complexes, and I will of course probe any reactivity towards carbon dioxide. Previously reported reactions, which hold some promise to be segments of potential catalytic cycles, will be revisited. The goal would be to continue these reactions to the remaining steps of catalysis. The catalytic efficiency of these systems will be documented. The project may extend to studying other metals, such as iridium and rhodium. I would now like to discuss some of my initial results from my first year. I have been working on the reaction of the cyclomethylated complex with acetylene to obtain this desired acetaldehyde complex. I have encountered issues such as solubility and formation of side products. Many different reaction conditions have been investigated to see how the outcome can be improved. So far, the following conditions are the most promising. A dioxane solution of the cyclomethylated complex is degassed and the acetylene is added in the headspace at a pressure of 1 atmosphere. The solution is stirred and after a few days, this acetaldehyde complex forms. Unfortunately, it reacts with another molecule of acetylene with elimination of hydrogen gas. This leads to the formation of these disubstituted acetylide complexes. Most of it adopts a trans configuration, but a cis isomer also forms. I have a gram scale reaction of this currently underway. After refreshing the acetylene headspace and stirring overnight a few times, a lot of this trans isomer precipitated out of the solution, as you can see in this picture. Almost all of the precipitate is this trans bisacetylide complex. I have been following the progression of the reaction using NMR analysis. The supernatant appears to contain all of the acetaldehyde complex. Currently, the ratio of complexes in the supernatant is 25 unreacted starting material to 25 acetaldehyde to 3 trans isomer and 22 cis isomer. Once all of the starting material has reacted, I will hopefully have a larger proportion of the acetaldehyde relative to the cis isomer. The supernatant can be collected and exposed to UV radiation to isomerize the cis isomer, as shown in previous research in the field group. Most of the trans isomer should precipitate out of the solution, and thus the supernatant would contain a relatively pure solution of the acetaldehyde complex. Some NMR spectroscopic scale solutions of this acetaldehyde complex were subjected to a headspace of CO2. Within 10 minutes, all of the starting material reacted. The NMR signals of this complex indicate that it is the novel metallolactone complex. Further work is required to isolate and fully characterize this complex. During my honors year, I unwillingly isolated this novel dinuclear complex, but never had a chance to study its reactivity towards acetylene and carbon dioxide. This complex presents two uncommon features in the NMR spectra, which I will show in the next slide. The spectroscopic scale reaction with acetylene has been investigated. Adding a headspace of acetylene to a benzene solution of this dinuclear complex has been observed to consume the starting material over 3 weeks. The proposed product is this relatively unstable dinuclear complex. The formation is theorized to occur with hydrogen gas elimination. On the left side, you can see the progression of the metal hydride proton-phosphorus decoupled NMR signals, and the bridging PME2 phosphorus NMR signal on the right. The signal for this bridging hydride is at relatively high field. The product also appears to have a bridging hydride corresponding to this signal, and also a bridging PME2 corresponding to this signal. After 21 days, the starting material is completely consumed. However, product degradation is also apparent. My plans for the second year of my PhD is to focus on iron chemistry. As part of this, I will revisit and continue some of the previous work done in terms of catalytic carbon dioxide coupling. Here are two examples. For the iron ethylene DIMP system, the previous work synthesized the ethylene complex and reacted it with CO2 to obtain this metallolactone complex. I will follow up with the remaining steps. First, the cleaving of the metallolactone to obtain this acrylato hydride, and then the elimination of the acrylic acid fragment and subsequent regeneration of the catalyst. Similarly, for the iron hydridoacetylide DIMP system, the reaction with CO2 to give the metallolactone has already been studied. I will investigate the remaining steps of this potential catalytic cycle. First, the cleaving of the metallolactone to potentially give this propiolate hydride complex, followed by the elimination of propiolic acid fragment and regeneration of this acetaldehyde catalyst. In my third year, I am planning to step away from iron and ruthenium complexes and investigate other metals. Ideally, the sort of systems I choose to investigate will be supported by similar work reported in the literature. For example, with nickel, there have been some studies into potential catalytic cycles. In this proposed cycle, there are a few unique ideas in some of the steps. You start with this nickel lactone and use methyl iodide to break the nickel-oxygen bond to give this iodide complex. This would undergo beta hydride elimination, forming a carbon-carbon double bond and releasing the ligand as methyl acrylate. This hydridoiodide would undergo reductive elimination to give this reactive zero-valent nickel complex. This would be quickly quenched by the ethylene and CO2 gas to regenerate the metallolactone complex. Similar nickel catalysis could be looked into in my third year. A major point to keep in mind is that most of the complexes presented have some degree of moisture sensitivity. However, the bottom example, a rhodium diethylene complex, uses water in the reaction with CO2. It leads to the hydrogenation of the ethylene to give this dinuclear complex. Conditions could be investigated to take this process further or make alterations that would allow the catalyst regeneration and product formation. And these are my references. I would like to thank you for your attention and hope that you found my presentation interesting.